Hello and welcome everyone. I'm really excited to have you all here with me for my presentation on streaming deep RL. So you may have heard of deep RL. So now we have a new kind of deep RL. It's called streaming deep RL. So something fascinating happened over the past 1 year here at Amii. So we solved a long-standing problem that unlocks new possibilities in AI. And I'm excited to talk about these new possibilities today. So my presentation is based on these two recent works led by Amii PhD students, one by Mohammad El Sayed, and the other one is by Gautam Vasan. So in these two works, what we do is that we solve a long-standing problem that unlocks a new way of understanding AI, a new scientific understanding. It unlocks new technological advancements and as well as new possibilities of applications. However, these two works are not isolated. They are a consequence of a long change of prior work by many people, including some people here today. So instead of just talking about the new algorithms and the work, I would rather like to take you on a journey toward streaming deep RL. So the talk is really about a journey towards streaming deep RL. And at the same time, I'd like to take an opportunity to thank some of the Amii students here for many discussions I had with them over the past years. All right. So this is the talk outline. I'm going to talk about the definition of streaming deep RL, and I will also motivate why we need streaming deep RL. And then finally, I'll talk about the recent advances that we made towards streaming deep RL. So the talk is in 3 parts, but before I start with the first part, I'd like to talk a little bit about myself, to explain myself, to make everyone understand where I'm coming from. So I'm a faculty member at Alberta, and I'm a Canada CIFAR AI chair. I'm also an Amii fellow, and my research area is at the intersection of RL and continual learning. So RL, as you may know already, that is about experiential learning, to interact with the world, to have more experience to achieve goals. Whereas in continual learning, what we work on is we want to make all the learners learn all the time rather than just once. So that's my research area. And my main research objective is nothing out of ordinary. It's the same as every other AI researcher. It is to understand the fundamental principles of intelligence. But a little bit difference that I think I have in my research focus than many AI researchers is that I use computational constraints as a guiding lens. And if you think carefully, this shouldn't be any surprise either. The whole AI research is about computation. So, and we can start with the definition of intelligence. The first one is adapted from Rich Sutton, which in turn is adapted from John McCarthy. So the definition is intelligence is the computational part of the ability to predict and control experience streams. And the original definition is the second bullet point, which is intelligence is the computational part of the ability to achieve goals in the world. So as you can see, intelligence is about achieving goals and to have capabilities such as predictions and controls to achieve goals. And it's also about learning from experience, to have experience, not just have passive data. But a big part of intelligence is computation. So it is a new way for us to even understand ourselves as intelligent beings. That what we are trying to do is we are trying to computationally process our experience in order to achieve goals. So computation is really a core driver in the quest for AI. It has always been. And core AI elements such as the models, the training algorithms, they are all computable functions. And the training of AI systems, as well as using them, they require a large amount of computational resource. And so much so that we have a new name for this term, computational resource. We call it compute. And compute is emerging as a new primary resource, comparable in importance to energy, right? So nowadays, we use compute to talk about productivity and progress. So using more computation is seen as an indicator of productivity. And now there is a key trend currently to do more using more compute. However, there has always been a silent hero here, which is compute efficiency. And that's the part that I have been focusing on. So the idea of compute efficiency is that we want to perform better per unit compute. Or in other words, we want to have the same performance as before, but using less compute. So that's the idea of compute efficiency. So if we do that, if we achieve the same performance using less compute, it frees up resources, right? And that allows us to then redeploy the resource and achieve even more performance, better performance. And it's not unsimilar to energy, right? So that's what we do as well with energy. More energy we use, that is seen as an indicator of progress, but at the same time, we also focus on energy efficiency is key. And this insight, this key insight is what I use in my own research. And that's why in my research, I focus on achieving AI under strict computational constraint. In my master's and PhD thesis, I worked on incremental learning, which is the original name for streaming learning. And in recent years, my research group has also used real-time robot learning as a test bed for compute-efficient algorithms. So I hope that clarifies my background, where I'm coming from. So, and I'm not alone, by the way, to take computational constraint as the key focus for research. Here at Amii, many researchers do the same as well. All right, so now I'll start with the first part of the talk, which is the definition of streaming deep RL. So I'd like to talk about streaming deep RL by contrasting with something that we already understand, which is offline learning. So in offline learning, we want to learn an AI model, and we want to deploy it in the real world to do something exciting. However, the way we train it is by using a stored data set. We have a large set of data, and we use it to train this AI model. But we do it in a separate phase from the deployment phase. Once it is deployed, we usually do not learn the model any further. So this is a typical offline learning pseudocode. So what we do first is we initialize the model weights, and then we load the data set. And after loading the data set, we want to go over this data set in offline learning as many times as we can afford. And each time, we shuffle this data set and pick a mini batch from this data set to make a model update. So the blue line here is about the model update using a gradient-based update based on a mini batch, a randomly sampled mini batch. And the orange lines here, they are all about handling the data, right? So there's a large data set there, so we need to do many things about it. And important part is to draw this mini batch randomly. So that's offline learning. As opposed to that, online learning, in online learning, we learn while deployed. We learn from an experience stream. There is no difference between a deployment phase and a training phase. So learning happens at the same time as the model is interacting with the real world. It is not trained in isolation. So this is the typical online learning pseudocode. Here, again, we initialize the model weights, and then we have now a loop inside which we are collecting experience. At each time step, so the loop goes over time steps, and at each time step, we are experiencing a sample ZT. And at the same time, we are making a model update, a gradient-based model update. So same blue line. However, if you notice, so the new thing here is, of course, the green line. But if you notice, there are still some orange lines. The reason is that typically, we still use the past data. So we start with an empty buffer, and we add the newly collected sample to the buffer. And instead of using the new sample directly to make a gradient update, we still randomly draw a mini batch and use that mini batch to make the model update, which means that the mini batch may not contain the most recent sample. So that might be seen as a problem. And streaming learning tries to address that. So streaming learning is also about learning from a stream of experience. So here we have a stream of experience coming from in the past. We have some experience. In the future, we are going to have some experience. But at the present, at time t, right now, we have ZT, a new experience sample. So wouldn't it be better if we use the most recent sample right away? So the idea in streaming learning is as soon as we see the sample, we want to use it to make a model update. And as we have already used it, we don't store it. So we don't store past experience in raw form. So that's the idea of streaming learning. And this would be the pseudocode of streaming learning. If you notice, this is much simpler. There is no orange line anymore because we don't need to. We do not store past samples. So we do have still this for loop going over time steps. At each time step, we experience a new sample, ZT, and we use that right away to make the model update. So that's streaming learning. Now, unfortunately, modern deep RL has not yet adopted streaming learning. And so we are going to talk about that. So now, before we talk about why we need to actually have streaming learning in this manner, we can talk about why we store past experience. So one reason we can say is that, well, offline learning is well understood. And in offline learning, we store all the data and go over it by sampling mini batches. Why don't we keep doing the same thing, right? So, and that is a reasonable argument because it's not uncommon in science to pick a solution from one area that is well understood and stable and apply to a new area. Another reason we can cite is that we can say that, well, we have memory experience in natural intelligence, right? With animals, we do have memory replay, so sounds like it might be a good idea that we also do that using AI. So that also sounds reasonable. However, one caveat is that in typical online learning, we replay the raw experience, whereas as animals, we do not replay raw experience. So that would be one big difference. However, most often, the reasoning that is given for using past experience in online learning is that if we replay the same sample multiple times, it gives us an opportunity to extract more information out of it. So the reasoning here is that, well, if you have streaming learning that's working well, why don't you then use the samples again and again many times to bring sample efficiency? So we're going to focus on this argument and investigate that a little bit by looking in the literature. But we are going to do it in two parts. First, we are going to look at the pre-deep RL era. In the pre-deep RL era, we had methods like TD, Q-learning, that often did not use actually neural networks or even nonlinear functional approximation. They used linear functional approximation or even tabular setup. And TD, Q-learning, they actually did not store past samples. They used data in a streaming manner. They made an update right after it experienced the sample. On the other hand, we also had batch or replay-based algorithms such as LSTD or DynaQ. Now, we can ask the same question again. Is it true that batch learning is more sample efficient? So here is a figure from Sutton and Bartow RL book. Here we are comparing different algorithms for a goal-reaching task. So the agent has to start from state S and reach the state G. And the optimal policy is to reach to go from S to G within 14 steps. And as you can see, all the different algorithms, they can eventually reach the goal state in 14 steps. So in x-axis, we have more experience, more trials. In y-axis, we have steps per episode. Now, what we can see here is that Q-learning, which is a streaming learning algorithm, it takes some time to reach the optimal policy. Whereas DynaQ, which is a replay-based method, it reaches the optimal policy much faster. So it is indeed true that in pre-deep RL era, we knew that batch learning can be more sample efficient than streaming learning. All right, so that's pre-deep RL era. How about the deep RL era? So deep RL is about using neural networks as a function approximator and learning the parameters of the neural network using gradient descent. And for batch methods, we have DQN, PPO, soft actor critic. These methods are well known and famous, still widely used. And for streaming learning, we can use Q-learning from pre-deep RL era and add neural networks as functional approximator. We could do that. Now, what happens when you compare these two? So this is a result from the DQN Nature paper. And here we are looking at, in blue, we are looking at the performance of DQN on a number of Atari tasks. And they do reasonably well. On the other hand, in red, we have the performance of Q-learning, a streaming learning algorithm. And looking at the number, we can tell that they are not eliciting an effective behavior in many cases. So the contrast here we are looking at is not about sample efficiency. Instead, what we are looking at here is stability versus instability. It's even mentioned in the paper that streaming learning can get stuck in a poor local minimum or even diverge. So that's the difference we see. So in short, we are not using batch learning for deep RL for sample efficiency, not necessarily. We have a bigger problem here. The problem is that streaming deep RL used to be unstable. So streaming deep RL did not work, and we call this phenomenon stream barrier. And batch or replay-based learning has served as a stopgap. So that's the situation we had until last year. All right, so now let's talk about the reasons why we need to solve streaming deep RL. Right? Like until last year, we didn't have it. But you may say that why we need to solve it though? It looks like a batch learning works, right? So if something works, why bother? So I'm going to give you the reasons. I'm going to give you 3 reasons for solving streaming deep RL. Okay. Number 1 reason is because natural intelligence also learns in a streaming manner. And we have evidence corroborated by experimental psychology as well as neuroscientific results. And the reason is obvious. If I have an experience right now, it might be wise to attend to it because it may contain information about the changes in the environment. So streaming RL allows fast adaptation. And that's why you will see that most well-known classic RL algorithms were streaming, such as TD, actor critic, Q-learning, or SARSA. And it's in fact not just a phenomenon about RL. If we look at classic optimization, supervised learning, or online learning, we'll also see algorithms that date back to 1951. They were about single sample updates. So in short, RL researchers have pursued streaming learning since the inception of the field, and it has long been considered as an important problem setup. And that's why overcoming stream barrier is an important scientific problem. However, you may not be interested in scientific understanding of AI, right? So these days, AI technology is advancing way faster than we are achieving scientific understanding of AI. So if you're interested in advancement of AI technologies, even for that, I argue that streaming learning is useful. So here is the second reason, and that has to do with scaling. So I already talked about scaling, right? So to use compute as a resource and to do better, do more, using more compute. That's the idea about scaling. And this is a famous figure from the GPT-3 paper. Here we are looking at, in y-axis, the loss, so lower the better. So performance better means going lower. In x-axis, we have amount of compute used. So we can see that as we use more compute, we can perform better by either increasing the size of the model or training the same model longer. These are the two ways you can spend more compute. So that's the idea of scaling. However, it might give us a wrong idea that if we just give more compute to current AI systems, they're going to just simply perform better. But that's simply not true. So in fact, we have seen in the past that scaling does not happen simply by giving more compute to current learning systems. Each time, we have seen that we needed new innovations. So innovations can be about unlocking new scaling regimes, such as utilizing test time compute for LLMs, or it could be about utilizing our silent hero, which is increasing compute efficiency. Again, it's about increasing performance per unit compute or achieving the same performance using less compute. And examples are effective initialization or normalization techniques, which are quite cheap to add to the current existing systems, but they allow us to have longer runs or use deeper models. So the proposition is that streaming learning is such a new kind of innovation that can help us achieve either a new kind of scaling or have more compute efficiency. So the way it's going to help us with efficiency is through time. If you think about it, in experiential learning, such as online learning or RL, if we spend time, we simply get more experience because experience is coming all the time, right? So we get experience over time. And that gives us new opportunities to improve our performance by using more compute. So this is a typical learning curve that we show in RL research. So in x-axis, we have time steps. Remember the for loop going over time steps. So each time we achieve a new experience. In y-axis, we have performance shown as returns. So higher the better. And this is quite typical. When experiential learning works. When RL works, we get better performance over time. In fact, on the top, you'll see that we are showing the wall clock time. So with 13 minutes, 40 minutes, 66 minutes, so more time we spend, the better the performance gets. And we are showing it in real time because these experiments were run on real robots. So that's the power of experiential learning, and streaming learning is an extreme form of experiential learning. So if we adopt streaming learning and if we make it work, then we would already be leveraging time-based scaling. So streaming learning is a great way of leveraging time-based scaling. Now, streaming learning also helps us achieve compute efficiency. So as we talked about compute efficiency, it's about performing the same but using less resource, which will free up compute, which will allow us to redeploy the compute and have better scaling. Now, if you think about streaming learning, you saw the pseudocode, how simple that is. It actually aims to use the least amount of compute throughput possible. So streaming learning, in that way, aims to learn with what I call atomic compute granularity. And on the flip side, if you think carefully, you'll notice that perhaps inability to do well with less resource could also mean not only a sign of inefficiency, but also a sign of poor scaling. And we have evidence for that. So here we are looking at the performance of 3 batch deep RL methods, PPO, TD3, soft actor critic. In x-axis, we vary the size of the replay buffer. So bigger the replay buffer, more resource it's using. And in the y-axis, we have the performance shown as return. So this is an experiment we have run using a simulated robotic task where the agent is learning to hop. So that's why it's called hopper. But any return that is below 1,000 return, they are not any kind of meaningful hopping behavior. So they can be called simply a learning failure. And here at this region, we see a regular scaling. With more resource, we perform better. However, when we are using small buffer or small mini batches, then we are hitting a performance floor. So learning is not working well. And of course, when the replay buffer is of size 1, then we are in the streaming learning paradigm. And over there also, learning is not working, which we call stream barrier. Now imagine if we had an algorithm that worked using only a single sample and achieved a performance way above 1,000 return, right? And we gave more resource to that agent, how well it could perform. So this shows that this is an indication that current deep RL methods, the batch deep RL methods, they are perhaps using the compute resource inefficiently. And that's why we would like to unlock better scaling with streaming learning by leveraging atomic compute efficiency. And that brings us to the third reason to solve stream barrier. So at the intersection of atomic efficiency and time-based scaling, we have a whole new set of application opportunities. Now think of all the smart devices that we carry around and the smart devices we have in our homes. We could make all these devices around us more adaptive and smarter, but they require on-demand compute, right? Because they have to attend to the now to be able to respond to the changes. And at that moment, you might not have access to the clusters. So in which case, you have to rely on device learning, which demands steep compute efficiency, because these small devices, they also carry small amount of compute. So we need to figure out then how to efficiently use this compute resource to continue learning. So then in short, we have these all around us, small computers that are available and accessible, and streaming deep RL could make all of them start to become adaptive and smarter. And that way, it would unlock and democratize ubiquitous AI. And by ubiquitous AI, I don't mean having ChatGPT installed in our smartphones. We're really talking about having local learning with greater control of our own AI, of our own models, and that way reducing reliance on remote clusters. So that's the third reason why we should solve stream barrier. All right, so now we are ready to talk about the recent advances we made toward streaming deep RL. Of course, the first thing we'd ask is why we have stream barrier, and what is causing it, in order to really understand what is the problem and then solve it. Well, the causes, it seems, are related to what we already know in continual learning and deep learning, which is that when you are learning with gradient descent, it can be unstable under non-stationarity when you are learning on non-IID data. And this instability is extensively studied in continual learning research, my research area, under the topics of catastrophic forgetting and loss of plasticity. So these are names. We give names to certain phenomena. Often it means that we don't fully understand really what is going on, and it's still true. We don't fully understand them, as is the case with many other problems or issues with neural networks. But we understand the symptoms very well. We can identify when things can go wrong. And one thing we notice is that instead of giving the learner data in a non-IID manner, if we give data in an IID manner, exactly the way the typical online learning algorithms work, then they face less instability. And the problem is that in streaming learning, we cannot do that. So streaming learning faces the most extreme form of non-stationarity. So it's really the same reason we have instability often in deep learning. We have it in streaming deep RL for the same reason, but more. And in continual learning research now, we have many different ways to figure out whether the learning is showing poor dynamics. For example, we may figure out that, well, the learning signals from different samples, they are interfering with each other, which we can identify using tools like neural tangent kernel. Or we can look at feature dormancy, or whether features are getting saturated, whether gradients are vanishing or exploding, or whether the curvature of the loss landscape is being lost. We have different ways of at least looking at the symptoms of instability. And a side note, by the way, there is a whole conference on these ideas, to looking at the symptoms and overcoming them. It's called Conference on Lifelong Learning Agents. This year, it is at UPenn between August 11 and 14. So I invite you all to attend the conference and witness all these new ideas on continual learning. Now, what do continual learning researchers do to remedy or mitigate these continual learning issues to some extent? So one idea is that we can go beyond gradient-based learning by having spatial weight initialization, reinitialization, perturbation, or search strategies being used. Some of those we used in our recent Nature paper last year. Or we can use also many other techniques, notably using different normalization techniques. So they are not only compute efficient, they also address instability. Now, the obvious question would be that how about we use some of these in combination to see if we can make streaming learning work? And that's what we do in our newest paper last year. We introduced an actor-critic method called action value gradient, or AVG. You can think of it as a simpler version of soft actor critic without replay buffers, without mini-batch updates. So it's a very simple form of an actor critic method in the deep RL setup. And on top of that, we add a number of carefully curated normalization techniques. We normalize at the input, we normalize at the output, and we normalize the penultimate activation layer. So after utilizing these normalization techniques, we see that when the batch learning algorithms, they hit a performance floor on a bunch of different tasks with small buffers, our algorithm, AVG, which is the blue star, it performs well using just a single sample in all these tasks, right? So it achieves effective performance in all these tasks. All these are simulated robotics tasks. So which means that AVG overcomes stream barrier, which is a good news. However, there is one caveat. We achieved this performance by tuning our algorithm differently for these different tasks. And that's a problem. It's a problem because we would like to also achieve time-based scaling with streaming deep RL. But how can we achieve time-based scaling if we are not sure that the hyperparameter configuration that we choose would sustain, would continue to work over time? So tuning overhead limits time-based scaling. In our next work, we overcome that. But we not only do that, we introduce a new class of streaming deep RL algorithms called StreamX. So what we do here is that we start with a number of classic RL algorithms, TD, Q-learning, SARSA, actor-critic, and we actually take their lambda variants, which use eligibility traces to enhance long-range credit assignment. And then we use on top of them neural networks because they are typically not used with neural networks, and a number of normalization and initialization techniques. But most importantly, we use a new optimizer. And the last one is critical. It allowed us to use all these StreamX algorithms perform well with the same hyperparameter configuration. So we not only overcome stream barrier, we overcome stream barrier for many different kinds of RL algorithmic regimes, and we do so using the same hyperparameter configuration. And I'm going to spend a little bit of time on the new optimizer. So what's the idea here? The idea here is that we look at the update size, and we are kind of worried about it. And the reason is it has to do with the instability that we face under non-stationarity. So when we are facing non-stationary data, what can happen is that sometimes there is a large update which can interfere with the signals that we learned from prior samples. So the idea is that when we encounter a large update, we're going to bound the size of the update. So now the question is how we are going to quantify an update size. Well, in optimization and batch learning, there are ways to do that. We can look at the error landscape, and then we can see whether while we are going downhill on the error landscape, we are overshooting the minimum, right? So we are going on the other side of the minimum. That indicates that the update size might be too large. And once that happens, when we have overshooting, it can exacerbate instability and interference. However, when we are doing single sample update, the notion of overshooting was not well understood or well studied. However, we can use things like using gradients in two subsequent time steps, or using the same time step data and making two updates and see whether they're aligned with each other. Right? So if they are not aligned with each other, if they're opposing to each other, that may mean that the first one was overshooting the minimum and the next one is now trying to correct it. And some of these ideas were introduced in my master's thesis as well as in a subsequent paper. And we utilize these ideas, but we also use a cheaper proxy of these ideas so that we don't really have to look at two different samples or two different updates. And the idea is that using this notion of quantifying a large update, we figure out when the update is too large, and we bound the update size for that large update. But if it is not a large update, we keep using the regular step size. And by doing that, we find that now we can overcome stream barrier. We can have not only overcome stream barrier, we can have quite stable performance. So here we are looking at a particular algorithm, stream SE, which is an extension of actor critic with our techniques. And we are showing the performance on 8 different robotics tasks. Here, what we see is there are different algorithms, 2 batch learning algorithms and 2 streaming learning algorithms. If you look at the streaming learning algorithms, they are not performing well, they are not scaling with time. Whereas soft actor critic, the purple one, is really performing well. It's a batch learning algorithm. That's not surprising. However, if we look at stream SE, the blue one, is also doing well in all the tasks. It is learning stably and scaling with time really well. So that's what we achieved in our recent work. We have overcome stream barrier. Now let's talk about, before wrapping up, let's talk about the new opportunities we have brought with streaming deep RL. Now we have all these classic RL ideas such as model-based RL, exploration ideas, intrinsic motivation or options. They are classically studied in the pre-deep RL streaming learning paradigm. And they're quite difficult to study in the deep RL paradigm because batch learning was quite expensive. And on top of that, if we study these additional ideas, they become even more expensive. Now we can revisit these ideas this time with streaming deep RL. Here is another opportunity. As we mentioned, streaming deep RL, they are compute efficient, which means that they actually free up orders of magnitude compute. So here I'm showing one of those 8 results again. So this is a typical result between a batch learning algorithms here and in this case a streaming learning algorithm. So over time they both perform well, they scale with time, but the batch learning algorithm is more sample efficient than the streaming learning algorithm because it performs better well ahead of time. However, note that the batch learning algorithm, soft actor critic here, actually uses 256 samples per time step to make an update. Whereas stream SE, a streaming learning algorithm, it uses only a single sample to make an update every time step. So it's an order of magnitude, multiple orders of magnitude difference in the use of compute. So if we instead showed performance in terms of compute used, performance would look like this. Stream SE uses much less compute. And in fact, I invite you to actually run our code. It's available online on your laptop using CPU cores. If you run soft actor critic on your laptop using CPU cores, it's going to take a while to finish any reasonable run. But for the same number of time steps, if you run stream SE, it would actually finish the whole run quite faster. So now the question is, as we freed up compute, how we are going to reutilize them. So we could add back batch updates. Now that we have atomic efficiency, adding back batch learning might work much better now. We could now allocate those resources for other RL ideas, such as model-based RL exploration options. Or we could learn many things in parallel, not just solving one control task, but we can learn many different parallel predictions using ideas like general value functions. All right, so time to wrap up. So in conclusion, stream barrier has been a long-standing problem in deep RL, and overcoming it unlocks new scientific understanding, new AI scalings, and ubiquitous AI applications. And we only have begun to scratch the surface of these possibilities by breaking stream barrier for the first time. And we also invite you to utilize the power of atomic efficiency with streaming deep RL. Thank you very much. Questions?
Can I use
it? Is that okay?
Hi. I love your idea in your Nature paper. I have a question.
Yes.
So one of the basic ideas in your paper was basically reusing all those neurons were not used, right? And all of those ideas after having the data is basically kind of whatever noise is already in the data, or maybe because I'm thinking that the data already has a nature, right? There are some connections, right? And there are maybe 5-10 modes that are most effective modes of deriving that behavior for the data. What's your thought, instead of using all these methods, which are beautiful, focusing on the data itself, capturing the most effective modes of that data, and then feed that to your model? For example, like using PCA, a simple model. What's your thought on or have you ever tried that?
There are many such ideas. One is PCA that we all need to try in the future. But the idea here is that we are now working on a new paradigm, and we may want to even look at PCA kind of algorithms in a streaming manner. So all these ideas are great. So what we are inviting is to reutilize them in a streaming manner, because still, if you look at all the data, there are cases where it might not be an option. You might not have an option to have all this data stored, and even if you have the option of storing all the past data, the way we are using them, I have shown results that indicate that we might be using it in an inefficient way. So what we are trying to convey is that there's a new lens through which we can look at those old ideas as well.
Thank you.
Thank you.
Hi.
Hi.
I hope you can hear me.
Yeah.
So let me take this off. So you talked about a bunch of ideas that you use, like sparse initializations and a different optimizer and a different suite of ideas.
Yes.
My question is really about, what do you think is the most promising research direction to look at to understand why this method of streaming works, and how, if you've done ablations, maybe you can touch upon that. Thank you.
Well, one thing I can definitely tell you is that you should go to the COLAS conference. That's exactly what we do over there. So we have tools to actually look at interference, and an obvious thing to do would be to use those tools to see what happens when we do streaming learning, how the interference is more happening in streaming learning, and when we use the new optimizer that we invented, exactly how it is helping. So that can give us some insight on what's happening there.
Yeah, and my question's mostly about, what do you think among the different suite of options that you've used, do they all have to work together for streaming to work, or is there one that works and then the other one just complemented?
Oh yes, of course. So we have ablation study in our paper. The most important one was the optimizer, but other ones were also important. So in order to achieve really good performance, you need kind of all of them to some extent. I guess there is an option to not have some of them and still have some effective performance, but I would definitely recommend addressing the interference issue using a solution like the optimizer that we invented.
Thank you. Thank you. That answers my questions.
Hi, so two things. You mentioned specifically CPUs, but on GPUs, the batch dimension is often essentially free for quite a bit, for 1 to even 2 orders of magnitude.
Yes.
So the compute efficiency argument doesn't seem really valid there.
So apparently, but it's also true that as we are not using the whole GPU anymore, it still frees up compute. It still frees up GPU resource, which we can use in parallel to do other things, such as in parallel we can try to improve the representation, learn many predictions at the same time. In the past, the idea was to do all those using batches, but now we can do it using single samples. So we can still scale up, but along other dimensions, not just through the batch size.
Okay. And then in terms of pure streaming, the continuous learning task looks very, very daunting if you don't have any explicit memory basis to replay things, that if you're going to make 1 billion sequential updates, you're almost guaranteed to have destroyed the earlier things. What are your thoughts for approaching that?
Right. So that's a fair point. And streaming learning is only a slice of many different things we could do. So we are studying here in these papers streaming learning in isolation. My thoughts is that we should have many different other things, such as memory replay. I am a fan of memory replay, but and this is also something studied in continual learning, which is how to do memory replay without using raw samples, right? So using some pseudo samples or imaginary samples. So all those ideas we still need to increase sample efficiency. We don't want to wait for billion steps. So we should bring everything that we have in our tool set. What I'm proposing is that we should do all those in the streaming learning paradigm so that we can utilize the compute efficiency we are leveraging here.
Hi there. So John touched on a little bit of what I was going to ask about, but obviously StreamX does well without a buffer, but the advancements in it, things like normalization, are probably going to be buffer agnostic. You already touched on this, but what is your intuition behind how much performance gain you might get by re-adding in a buffer? Did you do any comparisons with this algorithm compared to, it with a buffer, not having a buffer, and then the buffered without this normalization and other advancements?
We are working on it, but we are not alone. Many others are looking at it, and I invite you to also try it. It does help, and like many other things, we have to look at it more closely to make it work better. But so far it looks like it definitely works much better.
Yeah. Do you mind just quickly, can you quantify at all, like how much better do you think it is? I understand that this unlocks the ability to do streaming, but it could be the case that this is just better for everything, right? Do you think it's also the case for that?
So to quantify, to give you numbers, we need to wait for more rigorous experiments and then release the work.
Yeah. Fair. Thank you.
Thank you for the great talk. In the part about the new optimizer, you mentioned that one of the benefits it brings is that it identifies where overshooting is happening. So I'm wondering about where loss function is not something fixed and it changes over time. So the concept of overshooting the minimum kind of changes there.
Yes.
How do you deal with that?
That's a great question. So precisely because of that, we work with the single sample loss, not the overall loss function. So we are trying to do it in a strict sense. We are looking at the single sample loss and trying to prevent overshooting for each loss.
Hi, thank you for the great talk. On a related question, what's your opinion on test time training instead of test time computing?
Yeah, I mean, it is, of course, along the line of what I discussed, which is scaling with time. It's a time-based scaling, and we have been a fan of test time training all along. Actually, in standard RL, that's what we already do. right? So, and it is being looked at right now in advanced AI research areas like LLMs. And yeah, my opinion is that we will do a lot more in the future. It is a great way of utilizing more compute.
Thank you.
All right, so if no other questions, thank you so much.